Alright, and in this video we're going to continue talking about Taylor polynomials, but now we're going to try to extend this into many variables, just as we've done with many other things in multivariable calculus. So, with Taylor polynomials, we're only in multivariable, in the multivariable sense, we're only going to go up to degree 2. If you feel super ambitious, you could try to go into degree 3, have fun, but that's going to be beyond the scope of this course. Okay? So, just for a degree 1 multivariable function, if we have p of x is equal to all that in a single variable, all we have to do for the multivariable case is say, okay, well, we're going to have p1 of a vector x, right? Because now we have multiple inputs, and then, alright, so we're going to take whatever our function is and evaluate it at the point of interest, which is a vector, okay? And then, having studied derivatives for a little while, we're trying to think, okay, well, what is that analog of the first derivative in a multivariable case? Oh, it's the gradient. So it should be the gradient of f at a, and then times factor of x minus a as vectors. Okay, that's all the degree 1 case is going to be. Okay, so the degree 2 case should be just as easy, right? So if we do the multivariable case, all right, we have p2 of x is equal to f of a vector, and then plus gradient of f at a times vector x minus vector a, and then plus, okay, well, just as I thought about, how the first derivative extends in the multivariable case, I'm wondering, what about that second derivative, right? I don't quite know, but what I'm thinking is I'd probably still have that 1/2 out there. And then there's going to be an unknown thing. We haven't discussed the second derivative yet. And then we would just have the vector x minus vector a. Okay? So by the end of this video, these videos, and it's actually the very last one, we want to find out what this is, what that second derivative analog in the multivariable case is. Okay? Well, let's just maybe do an example and see if we can, figure it out. Okay, so we have a function f, right? And we want to find its second derivative. Okay, so, well, let's look at the gradient. Right, and if we do the gradient, I believe we get, and I'm going to use matrix notation just for change of pace. What do I get? 4x plus 3y. For the x component and for the y component, I believe I get 3x plus 4y squared. 4y to the third. Okay. And well, okay, so really all I need to do is, for the second derivative, if I know the first derivative is like a gradient, wouldn't it make sense to just do like the gradient of f? Okay, and I think I can do that, right? It has a derivative. It's a smooth function, or it's a, what is it, differentiable till degree 4. So we should be able to do this. Okay, and so if I do this, okay, well, now I need to take the derivative of f, and so I'm going to differentiate each one of these with respect to x, so differentiating the first function with respect to f, or x rather, is going to be 4, and then the second one with respect to x is going to be 3, and then with the second function then I need to also differentiate with respect to y, which is going to be 3 in the first function, in the first one, and then in the second component I'm going to get 12 y squared. Okay, so here I end up with a 2 by 2 matrix. Okay. Okay, so that's kind of fun. And this particular matrix, this second derivative matrix, we're going to actually give a nice name to. This is going to be called HF, or in other words, we're going to call it the Hessian, or Hessian, I don't know, I say Hessian, Hessian of F. Okay, and then just a side remark, when we talk about the gradient of F, some textbooks use JF as notation, meaning the Jacobian of F. Okay, so if you run across the name Jacobian, it just refers to the gradient. Okay. All right, so then just in general, now we're going to say that the Hessian and technically this is a matrix of a function f is the m by n matrix, such that when we create it, so a Hessian of f is equal to all the entries h, I, j, okay, such that the entries are equal to the second derivative of f with respect to xi and xj for all combinations of xi and xj. Okay, so the reason I got a 2 by 2 matrix above is because I had two variables. So it makes sense to say that if I have more than that, if I have more variables, it's going to be larger. Generally, though, if you have like the dimension says, if you have n inputs, you're going to get n outputs. Okay. And finally, just a question before we do a quick example. Is, I guess, when I wrote it, which notation did I use? When I did the second derivative, was it f in the off diagonal, so the diagonal elements were just fxx and fyy, but then what was it, fyx, fxy? Which one? Okay, and here's a surprise. It actually doesn't matter. The Hessian is symmetric. Okay, so I mean, there is a good order, but it really doesn't matter. When I did it, I believe I used this first notation, right? I said I put the functions and I put the functions in, or the variables of, so I put the second derivative of that contained x in the columns, and in the first column, and then the second column was the second derivative of f with respect to y. Okay, so I believe I used that first notation. All right, so just another quick example here. If I want to find the Hessian for this, I should probably find the gradient of f first. And so if I do this, I get y e to the x plus y to the fourth, and then e to the x plus 4xy cubed. Okay, and then doing the Hessian of all this, this is going to be another 2 by 2, and I'm just going to get y e to the x, and then e to the x plus y plus 4y to the third, and then e to the x plus 4y to the third, and then 12xy squared. Okay, and then when I put in the 0.12, I end up getting the matrix, that is to e plus 32 in the off diagonals, and then 48. So that symmetry property pops out nicely. And so that's kind of our second derivative in this context.